Hello and welcome to the LoRa Developer Portal Bits, Bytes, and Business series. Today's segment will show an overview of the LoRa Edge Reference Tracker. The overview of the LoRa Edge Reference Tracker will start with the components, features, and design elements that go into the tracker itself. It will also look at the housing. We'll then continue on to a reference block diagram of the device, as well as connections both internal and external to the device as far as data connectivity. It'll end up with a brief review of power consumption. The LoRa Edge Reference Tracker has multiple design elements. At its heart is the LR1110 with LoRa Basics Modem E firmware. In addition to that, the hardware has both an FR4 and patch antenna for GNSS. It has a built-in FR4 antenna for Wi-Fi and Bluetooth, as well as a sub-gigahertz antenna for LoRa communications. In addition to those antennas, it has an accelerometer for sensing whether there's motion or no motion, a Hall effect sensor, which is used to trigger the BLE pairing. The core micro unit is the STM32. It has the BLE or Bluetooth 5.0 integrated directly. It is sealed with water and dust resistance in its housing. It has two half AA batteries, also known as the ER14250. And all of these design aspects are available as design files for download. The features include 6 PCB layers for the main board. The regions supported cover many of the worldwide regions as defined in the LoRaWAN regional parameter specification. It supports 2 different output power, both for high power and high efficiency, and the receive and transmit RX-TX for the LoRa is handled through RF switch. Numerous applications could be handled with a device of this type, including asset location recovery and trace, inventory management, and asset loss and theft prevention. The LoRa Edge Reference Tracker has a host MCU, which is the STM32 mentioned previously, that's responsible for collecting up all of the device-centric functions. For example, collecting temperature or interacting with BLE. It interfaces to the LoRa Basics Modem E firmware, and the Basics Modem E firmware is responsible for handling all of the cloud services interface, including a LoRaWAN stack. And it also handles Wi-Fi, GNSS scanning, in addition to all of the radio planning and concentration for the LoRa interface to the cloud. On the board itself, you can see the sub-gigahertz antenna used for LoRa and LoRaWAN. The 2.4 gigahertz antenna here is shared for both the Wi-Fi scanning and BLE data interface. The PCB antenna built into the board for GNSS is complemented by the GNSS patch antenna, as well as the LEDs, and then the accelerometer that's used for motion sense. In the tracker block diagram, you can see the STM32 MCU connected to the LR1110 running the LoRa Basics Modem E firmware. The LR1110 is responsible for controlling the GNSS between the 2 different antennas. It can use one antenna at a time, selectable through a switch. There is also a switch between receive and transmit for the sub-gig antenna going into the LoRa input and output. Additionally, for the 2.4 gigahertz antenna, the Wi-Fi and BLE are set on a switch that when you want to do the Wi-Fi scan, you set it for the Wi-Fi input, and when you need to do BLE communications, you connect the switch alternatively to the BLE path. 32 megahertz oscillator is used to stabilize the acquisition of very precise GNSS scans. Additionally, there are outputs and inputs for the accelerometer, the Hall effect sensor for the magnet input, and there's also a user button that's accessible inside the device itself. For power consumption, we have a table here showing the sleep mode both with and without a supercap. The diagram here shows the configuration without a supercap, so that would be the smaller sleep current of 9 microamps. It increases to 16 microamps when you include the supercap, which can be useful for a power smoothing when your battery power goes low. The TX power for the high power power amplifier is 134 milliamps, and when on the high efficiency power amplifier, the output power is 86 milliamps. The transmit BLE is consuming 11 milliamps, and during the Wi-Fi scan, there's 12 milliamps of power consumption. You could also see similar 15 milliamp power draw for GNSS scan, and 5.7 when it's in the initial or it's when the final coherent search phase. These power draws are best in class as far as extremely low-level power draws to get GNSS and Wi-Fi scans during operation. This completes our overview of the LoRa Edge reference tracker design. Please see the LoRa developer portal for other content and videos related to LoRa and LoRaWAN development.